Hi folks, my name is Nikola and I would like to welcome you to my Neuromatch Flash Talk. I will be speaking about my latest work, which deals with various methods for the identification of latent quasi-stable EEG topographies. In particular, I tested out a few such options and tried to compare them. This is very much a work in progress and much more results are yet to come. Neuroscientists have been observing something called resting state networks for some time now. Those are temporal correlations of spatially distinct areas. We also believe they exhibit functional and clinical significance and are an area of active research. Typically, these networks are observed in fMRI, but naturally we may characterize their electrophysiological basis using EEG. A first such method is a classical microstate analysis, where the EEG signal is thought of as a sequence of limited number of quasi-stable topographies which define the latent space. In our work, we compare four such methods: classical microstates, PCA, ICA, and a decomposition based on hidden Markov models. We apply these methods on resting state EEG data and bootstrap data generated using four types of surrogate techniques: Fourier transform surrogates in three flavors and shuffle surrogates. We aim to answer several questions with our work. Primarily, we are interested in whether one of the four latent methods is superior to the other, and if so, why is that? Moreover, does it also mean that the superior method is better predictor for some EEG data features than some basic measures as a spectral power? How do these methods perform when we feed them fake data? Are the results comparable? And finally, can some latent decomposition statistics computed from EEG predict behavioral and cognitive performance? And where do the surrogates stand in this? For this, we use Lemon dataset, which is a publicly available dataset containing more than 200 healthy subjects acquired in Leipzig, Germany. From all the imaging modalities they provide, we utilize resting state EEG in both eyes open and eyes closed condition and a battery of 6 cognitive and 21 emotional behavior questionnaires. Now I will go briefly over the basics of the methodology used here. We start with the multi-channel resting state EEG signal, from which we identify the so-called global field power peaks. In these peaks, the multivariate signal has the highest standard deviation. In the next step, we will gather the EEG topographies in the peaks, hence we lower the number of time points in our data. Finally, we apply one of the four methods for latent decomposition, each of them yielding a set of predefined number of latent topographies. Next, we label the GFP time series using the latent states. Each time point represents a latent state with the highest topography correlation. Using this method, we segment the full time series into a categorical sequence of changing latent states. In our work, we always sought four states, which is typical in classical microstate analysis, and we were interested in comparing the latent topographies, the segmentations, and four basic statistics of latent decomposition. For each latent state, we computed the lifespan, the number of occurrences per second, its coverage, and the transition matrix. To start, we compare the resulting segmentations and latent topographies for all four methods and 5 data types. In the case of segmentation, we computed the Spearman correlation between pairs of segmentation for each subject, and the matrix here shows median across subjects. The lower triangle indicates the eyes closed paradigm, while the upper triangle shows the eyes open paradigm. As expected, in all four methods, the Fourier transform-based surrogates gave very similar segmentations with correlations 0.4 and higher, and the segmentation of real data using microstates, PCA and ICA are quite similar. Hidden Markov model segmentation is different from the other three methods, and the eyes closed and eyes open paradigms gave very similar results. As for the latent topographical maps, as expected, the microstates, PCA and ICA gave very similar results, while hidden Markov models again resulted in different latent topographical maps. Naturally, surrogates mostly reshuffle data in the temporal sense, but since we use multivariate surrogates, the resulting latent topographies are comparable to those found in the actual data. When comparing statistics on the latent states, meaning the coverages, lifespans and occurrences, we opted to perform a t-test indicating whether the value of, for example, lifespan is different between methods and/or data types. In the case of coverages, we can see some differences between eyes open and eyes closed paradigms. For example, a hidden Markov model has different coverages than other methods, but only in the eyes closed paradigm in state A. State B shows more pairs of differences, but this time only in eyes open paradigm. Similarly, state C and state D. The individual differences here are not that important, but they tell us that it should be possible to distinguish our paradigms using latent statistics. In other words, there might be a predictive power in these statistics. In contrast, lifespans are mainly similar between eyes open and eyes closed paradigms and more or less similar across states. They typically show microstates and hidden Markov model both having different lifespans than ICA and PCA, which display similar lifespans. In the next step, we try to assess the predictive power of various EEG features. Here, we try to predict whether the EEG time series were acquired in the eyes closed or eyes open paradigm using the spectral features. In particular, we compute band-specific envelopes in 2-second epochs, take the average over channels and use 5 typical bands: delta, theta, alpha, beta, and gamma. Hence, our input consists of 5 features per data point. Firstly, we create a random train test split with 30% test data and then train various classifiers and assess their performance by the area under curve. To minimize the effect of a random split, we evaluate 2 classifiers, the logistic regression and the Gaussian processes classifier, using repeated stratified k-fold cross-validation with 5 folds and 20 repeats each. In the case of logistic regression, we obtained an average area under curve of 0.75, while for the GP classifier the average area under curve is 0.76, so practically the same. Now we play the same game, but instead of intrinsic spectral characteristics, we compute the latent decomposition, then compute the segmentation statistics and use these as an input to our classifier. In particular, we use each state's lifespan, occurrence and coverage, so totaling at 12 features per data point. In our primary assessment, the classifier scored slightly higher than in the case of spectral features. In particular, hidden Markov model derived features were the most helpful in predicting the data paradigm, with the best model reaching 0.81 area under curve. As before, we computed the stratified k-fold cross-validation, and as before, the hidden Markov model derived features built the best performing model, averaging just below 0.8 compared to the spectral features averaging in 0.75. In the next step, we will also compare the performance of spectral features and latent classifiers on surrogate data. Currently, there are no conclusions, and we will continue our efforts in disentangling the posed questions. I would like to thank you for your attention, and I'm looking forward to seeing you on the Discord channel.